Pneumatics. What is pneumatics?
Well, to keep things simple, pneumatic systems basically just use compressed air to do work. And to understand pneumatics, you really only need to understand one equation, and that equation is the ideal gas law, which is very simple. That is just P times V equals nRT. And what are these values? Well, P is just pressure, V is volume, N is the number of moles, R is the ideal gas constant, and T is absolute temperature like Kelvin or Rankine.
And so in any system, we can change the pressure, we can change the volume, we can change the temperature. And you can change N by increasing the amount of gas or decreasing the amount of gas. So when we say the number of moles, we mean literally the number of atoms in the system. And the ideal gas constant is just a constant number like pi. And so in this case, the ideal gas constant is 8.134 joules per moles per Kelvin. And this equation is really all you need to understand how pneumatic systems work. But I actually prefer the equation written a different way. And so let's go ahead and write out the equation. PV equals nRT. But let's instead put temperature on the other side of the equation. So if we divide by temperature on both sides, we now get the pressure of any system times the volume of that system divided by the temperature of that system will be equal to the number of moles in that system times the ideal gas constant. And there are some very important implications here. And to explain that, let's draw a balloon. And so we can even label this as our balloon. The pressure inside this balloon multiplied by the volume of this balloon divided by the absolute temperature of the air inside the balloon will be equal to the number of moles in the balloon multiplied by the ideal gas constant. But what's important is it is a balloon, which means the air inside is trapped, which means the number of moles is also constant. And so what happens if we take that balloon and we squeeze it? And this balloon doesn't really look like a squeezed balloon, does it? But we'll go ahead and just label it squeezed balloon so that we all know. And so assuming the balloon doesn't pop, in each of these scenarios, the number of moles is constant, and obviously the ideal gas constant is constant. And so what is changing? Well, I had an original pressure. I had pressure 1 over here on the left. And I had an original volume on the left, and we had some original temperature here on the left. What have I done? Well, all I did was squeeze the balloon. Well, squeezing the balloon will change my pressure, which will then in turn change the volume, and realistically, it will probably change the temperature slightly as well. But in both these situations, the number of moles stayed the same. The number of atoms of air is the same in both balloons, and the ideal gas constant stayed the same. And so both of these examples equal N times R, and therefore equal each other. And let me see if I can explain this a little bit better. Let's say our N times our R, so our number of moles multiplied by our constant is equal to exactly 24. It would be joules per Kelvin. And it would be joules per Kelvin because R is joules per mole per Kelvin, and we're multiplying N by R, and N is number of moles. So moles is on top and moles is on bottom, and so it will cancel out, and you'll be left with joules per Kelvin with N times R. But let's go ahead and just ignore units from here. Well, in our first system, if we say that our pressure is 6, just 6 psi, but again, let's just avoid units for now. So our pressure is 6, and let's say our volume is 6. Well, then our temperature would have to be 1.5. And it's pretty unrealistic to get an absolute temperature of 1.5 in a balloon, but this is just an example, so let's just go with it. And I get 1.5 because 6 times 6 is 36, divided by 1.5 would give me an N times R of 24. But in the second system, we increased the pressure. And let's say we increased the pressure to 12. Well, if we increase the pressure, you can expect the volume and the temperature to change. And so let's say the volume changes to 5. So it gets a little bit smaller because we increased the pressure. It shrunk it down just a little bit. And the temperature would therefore have to change to 2.5. And how do I get that? Well, 12 times 5 is 60, and we'd have to divide by 2.5 to get 24 again. And so the point is these have to equal each other. And if I were to say create a third system where I squeezed the balloon even more, so the pressure went all the way up to 24, and let's say the volume decreased to 3. Well, then I would have to divide by 3 to cancel that out to get a final value of 24 once again. And so let's go ahead and label each one of these actually. So the unsqueezed balloon is scenario 1, we'll say. And then this is scenario 1 as well. And the squeezed balloon is scenario 2, S2. And then this one is scenario 3, which we did not draw. But in all three scenarios, assuming I didn't pop the balloon or did anything that caused the amount of air inside the balloon to change, then the number of moles times the constant has to be the same.
So what is it that I want you to take away from this video? Well, basically all I want you to take away is 3 main things. The first is the ideal gas constant, R, does not change. The second thing is if the amount of gas in the system doesn't change, then N times R is also constant. And finally, if pressure, volume, or temperature change, the other variables must also change to keep the equation true.
And if you understand these 3 things, you understand everything you need to be able to solve for a pneumatic system.